Okay, so let's go and do an example of triple integrals. We're gonna, in this example, we're gonna set up the triple integral of some function. We're not going to evaluate it, so let's just call it f of x, y, z. And this time our solid S is going to be the sphere. So a general region, right? It's obviously, it's not a box, it's a sphere, and it's a sphere, right? The entire sphere, right? So less than or equal to 1. It's the sphere, the solid sphere that we're integrating over. And remember, if this were density, if this were a density function, if this were giving me grams per centimeter or something like that, then the triple integral would give me the total mass of the sphere. So the question asks us to do this in 2 ways, well actually 4 ways. We're asked to do it in part A as a type 1 solid, and then to do that in 2 ways, right, in each of the 2 orders for that shadow region D. And B then asks us to do it as a type 3 solid, again in 2 ways. So we're doing here 4 of the 6 orders of integration over this sphere. So if we go down here, and let's take a quick look at the sphere as I have drawn it. So if this is our sphere, x squared plus y squared plus z squared is equal to 1, and we solve for z, then z can be expressed in terms of x and y as the positive and the negative roots. So the top portion of the sphere, the upper function, right? You remember type 1 is bounded above and below. So the above boundary is the red sphere, the red half sphere, and the blue half sphere is the boundary below. And then we're looking at, well, where is our shadow region D? Well, D is always on the xy plane. And if our integral, if our solid cuts right through it, well, our region D just happens to be right smack dab in the center of the sphere. But that's fine. We can integrate over that region D. And so if we look, how are we going to find that region D? Well, that region D is going to be in this situation when z equals 0, right? If it's in the xy plane, it's where z equals 0. And if z is equal to 0 in the equation x squared plus y squared plus z squared is equal to 1, that's the boundary of it anyway, then if z is 0, well, guess what happens? Then we get this. X squared plus y squared is equal to 1. So our region D, if we come down here in the xy plane, it's just the unit circle. Okay, so let's think first of all what we have to do. We have to create this inner integral first. This inner integral is going to be with respect to z, because we're type 1. This inner integral is going to go from the lower boundary. You're imagining z values going from the lower boundary to the upper boundary. And so they're going from the negative root of 1 minus x squared minus y squared to the positive root of f of x, y, z dz. There's the inner integral. Then step 2 is going to be to set up this outer integral, this one here, to set up that outer integral with respect to our region D. And that's what we're going to come down here and do. So if we do this, that region D can be set up in 2 ways. It can be set up in 2 ways. This is what we would have called a type 1 way of setting it up, and this is what we would have called type 2. And so in type 1, we're looking for constant inequality on x. X goes from minus 1 to 1. And then for any fixed x value, you're looking where y goes. And y goes for any fixed x value. Y travels from the lower root to the upper root. Again, the y can be solved for in terms of the root functions, and here they are. There's the lower one and there's the upper one. If we do that, if we set this up as a type 1 integral, then the constant value is on the outside. Constant values on the outside, they were dx. The function in terms of y, right, this inequality here, these inequalities there, are in terms of y, and that inner integral is just this guy, which is still there. We're going to do the same thing. We're going to do the same thing now, but as a type 2 integral. As a type 2 integral, let me change color here. As a type 2 integral, you want constants for your y. So y also goes from -1 to 1. Y goes from -1 to 1. And for any fixed y value, you want to see where x goes. And x goes for any fixed y value from the negative root, but solved in terms of x, right? X is minus the root of 1 minus y squared, and x is plus the root on the other side. So you're going to set up that exact same thing. So the inequalities in terms of y, the constants, y is now on the outside. The inner integral, no, the middle integral is in terms of x, and those are the bounds that match those inequalities in terms of x. And the innermost integral is the same because that is the type 1 solid, right? We're talking about type 1 and type 2 regions, but this is a type 1 solid that we're still working under, the two ways. So that inner integral is because we've got a type 1 solid. That was part A. Part A says set it up as a type 1 integral above and below in each of the two ways for the region D, the shadow region. So let's do this quickly now for B, a type 3 integral where we've got a right boundary and a left boundary. So this is the right and the left. So this here is the same sphere that I have drawn by solving for y. Solving for y so that I get a right function and a left function, which gives me the sphere, the half sphere in red and the half sphere in blue as the left boundary. That inner integral is then in terms of y, not in terms of z anymore, because our boundary functions are in terms of y. And so that inner integral goes from the leftmost value in terms of a function to the rightmost boundary function. And then we have the same issue. We have a double integral left over this region D. This region D is the region that is shaded here. And that region D is no longer on the xy plane. X and z are the dependent variables. So our D region is now a region in the xz plane. So that region D, again, has two ways of being set up. The xz plane is the plane where y equals 0. And if we take the sphere, or the boundary of the sphere, and we put y equal to 0, then we get the equation of the boundary sphere, boundary circle here, the shadow circle here. And there's two ways. There's two ways analogous to what we just did before. So here this is set up as a type 1 planar region this time. We're still in a type 3 solid, a type 2 planar region. And let's just double check the inequalities that we have here. X goes from -1 to 1. X is the constant, so there is it is as the outer integral. Y goes from, Z. Z for any fixed x value, Z goes from, let me do that in another color to make it match. Z goes from the lower root to the higher root, so there is the z integral dz, and the inner integral is still the exact same one from up here in terms of dy. The other way here as a type 2 integral, x goes from -1, I keep saying the wrong letters, z goes from -1 to 1. There is the z integral here now with respect to z. X goes, I have to concentrate so hard to say the right letter, x for a fixed z value, x goes from minus the z root to positive the z root, so there is the x integral, and then the innermost integral is exactly the same one as above because we are doing this all as a type 3 solid. There would be two more ways of doing this, right? And we could do this as a type 2 solid, but one, the question doesn't ask, and two, I think you probably get the point of this now, but there are 6 ways total. There are 6 ways total of expressing these kinds of triple integrals over a solid.